In this video, we're going to talk about how to solve work-related problems as it relates to calculus. So let's start with the basics. How much work is required to lift a 5-kilogram book 2 meters high above the ground? So if you wish to calculate the work done by a constant force, the work is equal to the force multiplied by the displacement. And you need to know that force is mass times acceleration. And the acceleration in the y direction is g, which represents gravitational acceleration. So for this problem, replacing F with mg, the work required to lift up something is mgd. M is the mass in kilograms, that's 5 kilograms. G is the gravitational acceleration, that's 9.8 meters per second squared. And d is the distance in meters. 5 times 2 is 10, and 10 times 9.8 is 98. So the answer for part A is 98 joules. And that's it. Now for part B, how much work is required to lift a 30-pound box 4 feet off the ground? The units are different. Now, when you see the weight in pounds, this doesn't represent mass. Weight is a force. So all we need to do is use this equation. So the work done is going to be the force of 30 pounds multiplied by a distance of 4 feet. So 30 times 4 is 120. So it's going to be 120 foot-pounds, which is another unit of work. Number 2, find the work done in pushing a car a distance of 15 meters with a constant force of 500 newtons. So anytime you wish to find the work done by a constant force, you can use that equation. So the force is 500 newtons and the distance is 15 meters. So we could just multiply those two numbers. And don't forget, a newton times a meter is a joule. So the work done is going to be 7,500 joules. And that's all you need to do for this problem. Number 3, a variable force in newtons acting on an object is represented by the function f of x is equal to x squared minus 4x plus 7, where x is the distance in meters from the origin. How much work is required to move the object from x equal 1 to x equal 4? The work done by a variable force is the definite integral from a to b of the force function times dx. So in this case, a is 1, b is 4, based on the values that we see here. F of x is x squared minus 4x plus 7. The antiderivative of x squared is x cubed divided by 3. And the antiderivative of x is x squared over 2. And the antiderivative of 7 is 7x. So let's evaluate it from 1 to 4. So if we plug in 4, it's going to be 4 to the third over 3. And then 4 divided by 2 is 2. And then times 4 squared plus 7 times 4. And then we need to plug in 1. So it's going to be 1 over 3. And then 2x squared, so 2 times 1 squared, plus 7 times 1. Now, 4 to the third is 64, and 4 squared is 16. 7 times 4 is 28. And on the right, we have 1/3 minus 2 plus 7. So this is 64 over 3. 2 times 16 is 32. And if we distribute the negative sign, it's going to be negative 1/3 plus 2 minus 7. So now let's combine like terms. So we can combine these two. 64 minus 1 is 63. So that's 63 divided by 3. Negative 32 plus 28 is negative 4, and 2 minus 7 is negative 5. Now 63 divided by 3, that's 21, and negative 4 minus 5 is 9. 21 minus 9 is 12. So the answer is 12 joules. Number 4. A force of 50 pounds is required to hold a spring stretched 5 inches beyond its natural length. How much work is required to stretch it from its natural length to 10 inches beyond its natural length in foot-pounds? So let's talk about springs. So let's say this is a spring that it's in its natural state. In order to stretch a spring, you need to exert a force. And in order to hold it at this position, you have to apply a certain force. The spring wants to snap back, and so there's a restoring force that wishes to pull it back. So to calculate the force that's required to hold it at the new position, that force is equal to the spring constant times x, where x is the distance between its natural length and its current length. Now k is a constant, and k can be found by taking the force divided by x. So in this problem, we need to find k. 50 pounds of force is required to stretch the spring 5 inches beyond its natural length, so x is 5. And 50 divided by 5 is 10. So k is 10 pounds per inch. So now that we have k, we can write the force as a function of x. So it's going to be k times x, or 10x. So that's the force required to stretch the spring at any distance x from its natural length. So if we want to stretch it, let's say 20 inches from its natural length, the force would be 10 times 20, or 200 pounds. So now we can calculate the work. The work done is going to be the definite integral of f of x dx. So we wish to calculate the work required to stretch it from its natural length, that's when x is 0, to 10 inches beyond its natural length, which x is 10. X is the distance from the natural length to its current position. So the work is going to be the integral from 0 to 10 f of x, which is 10x times dx. The antiderivative of 10x is going to be 10x squared over 2. And so 10 divided by 2 is 5. So it's going to be 5x squared evaluated from 0 to 10. And that's 5 times 10 squared minus 5 times 0. 10 squared is 100. And so it's 5 times 100, which is 500. And the units are pounds times inches. Now we wanted to convert it to pounds times feet. So 1 foot is equal to 12 inches. So the unit inches will cancel. And so this becomes 500 divided by 12 foot-pounds. Now we can reduce 512. So 500, we can write that as 125 times 4. And 12, we can write that as 3 times 4. And so we could cancel a 4. And so the final answer is going to be 125 over 3 pounds times feet. And this is it. Number 5. A force of 60 newtons is required to hold a spring that has been stretched from its natural length of 12 centimeters to 17 centimeters. How much work is done in stretching a spring from 15 centimeters to 20 centimeters? So the first thing we need to do is calculate K. So we know that the force required to hold a spring beyond its natural length is k times x, where x is the distance between where you're holding the spring and its natural length. So let's say this is the natural length of the spring. That's 12 centimeters. And we stretched it beyond its natural length. So this distance here, that's x. 17 is the total distance between point A and point B. X is the difference between 17 and 12. So in this example, x is 5 centimeters when a force of 60 newtons is applied. So 60 equals k times 5. So k is going to be 60 divided by 5, which is 12. And it's newtons per centimeter. Now let's get k in newtons per meter. So let's convert 5 centimeters to meters. 1 meter is 100 centimeters. So 5 divided by 100 is 0.05 meters. Now k is F divided by x. So we have 60 newtons divided by 0.05 meters. And so that's going to be 1200 newtons per meter. So that's the force in terms of x as a function, it's k times x, or 1200x. So the work required is going to be the definite integral from a to b, but we're comparing these values to its natural length of 12. So the difference between 12 and 15 is 3 centimeters, but in meters, that's 3 divided by 100, so it's 0.03. And the difference between 20 and the natural length of 12 is 8 centimeters, or 0.08 meters. And then it's going to be f of x dx. So the antiderivative of x is x squared over 2, evaluated from 0.03 to 0.08. And 1200 divided by 2 is 600. So we have 600x squared. So now let's plug in 0.08. So it's 600 times 0.08 squared minus 600 times 0.03 squared. 0.08 squared times 600, that's 3.84. And 0.03 squared times 600 is 0.54. And so the final answer is 3.3 joules. And so that's the work required to stretch the spring from 15 centimeters to 20 centimeters. Number 6. An 80-foot long rope with a weight of 3 pounds per foot hangs over the edge of a building that is 200 feet high. How much work is required to pull the entire rope to the top of the building? So let's draw a picture. So let's say this is the building, and here we have a rope that hangs on the building. Now let's say this is 0 and this is 80. Let's make this the origin. So we want to lift that entire rope to the top of the building. How much work is required? Well, we know that work is equal to force times distance. And force is basically weight. Weight is a force. And you could describe the weight as being the weight density of the rope, which is pounds per feet, times the length of the rope, which is in feet. And if you see it that way, notice that the units feet cancel and it gives you the weight in pounds, which is a force. Now this expression is similar to F is equal to kx. X can be measured in feet. K, for the spring constant, can be measured in pounds per feet, because K is F divided by X, where if F is in pounds and X is in feet, K is pounds per feet. So the generic force equation is going to be the weight density of the rope in pounds per feet times the length of the rope, or the distance that the rope travels, which is x. So in this case, it's 3 pounds per feet times x. So that's the function that tells us the force that's required to lift up the rope in terms of x. Now, to calculate the work required, it's going to be the definite integral from a to b f of x dx. Now, we need to determine what a is and what's b. A is going to be 0, b is 80. So it's going to be from 0 to 80, f of x is 3x, and then dx. So the antiderivative of 3x is 3x squared over 2, evaluated from 0 to 80. So that's going to be 3 over 2 times 80 squared minus 3 over 2 times 0 squared. Now 80 times 80, that's 6,400. If we multiply that by 3 over 2, this will give us 9,600. And the units is going to be pounds times feet for this problem. Now let's try another example, part B. How much work is required to pull half of the rope to the top of the building? So let's draw a new picture. So let's say this is the building, and let's say this is the rope. Now it's best to break it up into two parts. So the rope is 80 feet long, and we need to move it up by some distance x. Now, you want to calculate the work that's required to lift the upper half and the bottom half separately. So let's calculate the work that's required to lift the top portion of the rope. Now, this entire part is moving to the top of the building. So the entire first half of the rope is going to be lifted to the top. So we can calculate that answer using the same technique as part A. And so it's going to be the integration from 0 to 40, 3x dx, because that part is going to be lifted up by x. So it's going to be 3x squared over 2, evaluated from 0 to 40. So that's 3 over 2 times 40 squared minus 0 squared. 40 squared is 1,600 times 3 over 2, so that's going to be 2,400 pounds times feet. Now, to calculate the work that's required to lift the bottom half, you need to realize that the bottom half doesn't move by a variable distance x. All of it moves exactly by 40 feet. Because this part, it's not going to go over the top of the building. It's still going to be hanging along the side of the building. So that entire segment moves up by a distance of 40 feet because that's half the length of the rope. So everything is going to be the same, but the distance here won't be x, it's going to be 40. Now we're going to integrate it from 40 to 80, but it's going to be 3 instead of x, so it's not going to be 3x, but 3 times 40 dx, so which is 120. The antiderivative of 120 is 120x, evaluated from 40 to 80. So to 120 times 80 minus 40. 80 minus 40 is 40, and 40 times 120 is 4,800. So if you add up these two values, 2,400 plus 4,800, that's going to be 7,200, with the units pounds times feet. And this is the final answer. Another quick way to get this answer is it's always going to be 3/4 of the answer in part A. So in part A, it was 9,600 pounds times feet to lift up the entire rope to the building. Now, if you want to lift up just the first half to the top of the building, it's going to require 3/4 of the work required to lift up the entire rope. It takes more work to lift up the first half than the second half, because as you're lifting up the first half, you're pulling up the entire rope. When you're lifting up the second half, it's just the bottom portion, which is a lot easier to do. So when you begin to lift up the rope, it's hard to lift it up at the beginning, but towards the end it gets easier because there's less of it that's hanging down. So anytime you wish to calculate the work that's required to pull half of the rope to the top of the building, it's going to be 75% of the work required to pull the entire rope to the top of the building. 9,600 times 0.75 is 7,200. Number 7. How much work is required to lift a 300-pound crate up a distance of 200 feet using a rope that weighs 4 pounds per foot? So there's two parts. The first part is we need to lift up the crate. So how much work is required to lift up a box or a crate? The work required is simply force times distance. And so the force is the weight of the crate, which is 300 pounds, and we're lifting it up by a distance of 200 feet. So it's going to be 300 times 200, and that is 60,000 pounds times feet. So that's the work required just to lift the crate. Now we need to calculate the work required to lift up the rope by a distance of 200 feet. So first, we need to write an equation for the force that's required to lift up the rope in terms of x. And it's going to be the weight density in pounds per feet times the distance that we're lifting it up. So the force equation, it's going to be 4 pounds per feet times x, or simply 4x. So the work required is going to be the definite integral from a to b. So from 0 to 200, we're going to integrate 4x dx. So the antiderivative of 4x is 4x squared over 2, evaluated from 0 to 200. So 4 divided by 2 is 2. So we have 2x squared. And so that's going to be 2 times 200 squared minus 0 squared. 200 squared is 40,000. If we multiply that by 2, that's going to give us 80,000 pounds times feet. So the total work required to lift up the crate along with the rope is going to be the sum of these two numbers. And so 60,000 plus 80,000 is 140,000. Let's see if I can fit that here. So it's going to be 140,000 pounds times feet. So that's the total work required to lift up the crate and the rope. You just need to calculate the work required for each item separately and then just add it up. Let's work on this last problem. An inverted circular cone with a height of 12 meters and a radius of 5 meters is filled with water to a height of 9 meters. How much work is required to empty the tank by pumping all of the water to the top of the tank? Well, let's draw the inverted circular cone. And then this is going to be the water level. Now the cone, it has a radius of 5 meters and a height of 12 meters. The height of the water is 9 meters. And so this distance here between the top of the cone and the top of the water level, that's 3. That's 12 minus 9. How can we determine the work required to pump all of the water to the top of the tank? The generic formula that you could use is this equation. the work required is going to be the density of water times the gravitational acceleration times the definite integral from a to b of the volume of a cross-section as a function of x times the displacement, and then dx. So if we draw a cross-section, which is going to be the shape of a cylinder with a height of delta x, we need to write an expression that tells us the volume of that cross-sectional cylinder. Now, if you're wondering how to get this equation, or at least the foundation of it, here's what you could do. We'll get back to this cross-section. We know that work is equal to force times distance, and force is mass times acceleration. The acceleration in the y direction due to gravity is g, gravitational acceleration. So you can replace F with mg, and d is basically the displacement. Now, density, which is indicated in physics by the rho symbol, is mass over volume. So mass is density times volume. So the work is going to be density times volume times gravitational acceleration times displacement. And so it's going to be density times gravitational acceleration times the integral of the volume as a function of x times the displacement as a function of x dx from a to b. But that's where this equation comes from, if you wanted to know that. Now, this cross-sectional cylinder has a radius r, and the height we said is delta x. The volume of a cylinder is pi r squared times the height. Now, the height is delta x. We need to write a relationship between r and x. And we're going to use similar triangles to do that. So we have this triangle, and this part of the triangle, what is the height of that part of the triangle? Well, first, this cross-sectional area, we're going to say it's x units deep. Therefore, this portion has to be 12 minus x. So this is going to be 12 minus x, and the entire height of the triangle, the large triangle, that's going to be 12. This part is 5, and this portion here is r. So for the small triangle, we could say the ratio is r over 12 minus x, and for the large triangle, it has a ratio of 5 to 12. If we look at the radius to the height. So if we multiply both sides of this equation by 12 minus x, we can see that r is going to be 5 over 12 times 12 minus x. So the volume as a function of x is going to be pi times the radius squared, that's 5 over 12, 12 minus x squared, and the height is delta x. Now when dealing with integrals, we're going to replace delta x with dx. 5 squared is 25, 12 squared is 144. So the volume is going to be 25 pi over 144 times 12 minus x squared dx. Now what about the displacement? So this cross section, this little piece, we're going to pump it out to the top of the tank. So we're going to lift it up by a distance x. So the displacement function for this problem is simply x. Now let's plug in everything to our definite integral. So the density of water in kilograms per cubic meter is 1,000. G is 9.8. And then we have the integral from a to b, where those values represent the depth of water. So the depth of water ranges from 3 to 12. The top part of the water is 3 meters below the top of the tank, and the bottom part is 12 meters below the top of the tank. So we're going to integrate it from 3 to 12. Now at this point, I don't need this picture anymore because it's taking up space. So let me just rewrite this expression on the left side. So it's going to be 1,000 times 9.8 times the integral from 3 to 12. And the volume function is what we have here. That's 25 pi over 144 times 12 minus x squared. And the displacement, we said, is simply x for this problem. So we're going to add x here. Now, if you type this expression into your calculator, you should get this as your final answer. 6.82 times 10 to the 6 joules. And that's it. Hopefully you have one of those graphing calculators that has the ability to evaluate definite integrals. If you need to do it by hand, you need to FOIL this expression and then distribute x. You can move this constant to the front and then integrate the polynomial from 3 to 12. And then you should also get this answer as well, if you do it correctly and avoid making mistakes. So that's it for this video. Thanks for watching.